Now let's move to dynamic quantities. The prototype and the scaled model are said to have dynamic similarity if the net forces at the homologous points in the two are related by a constant scale factor Kf. However, the force at a point in a system is related to kinematic quantities. Newton's law of motion relates the net force F on the element to its acceleration A and inertia. If Kf, Km, and Ka are the scale factors for forces, masses, and accelerations respectively, we can write F is equal to Ma, which gives us Kf is equal to Km into Ka, or converting into pi number, that F divided by Ma is a pi number. Now, we can manipulate them like this. Kfi gives you Km into Ka. But Km is related to the density times the volume. Mass is rho times the volume. So Km is like K rho KL cubed. Similarly, the acceleration is kv square by kl. How? Recall from Euler acceleration formula, the convective acceleration was v dv by ds. v dv by ds. v scaled by kv, dv by ds is scaled by kv divided by kl. So that k acceleration becomes kv square divided by kl. So that kfi is equal to k rho kv square kl square. And from this, we obtained a pi number. So pi is equal to force divided by rho v square L square. Here we have listed various dynamic quantities like force, momentum, torque, work, power, pressure, and shear stresses. We have first written the scale factors in terms of K rho, KL, and KT, and then in terms of K rho, KL, and KV. And then from these scale factors relation, we have developed the pi numbers. The question that now needs to be answered is how the modeling rules are obtained. The modeling rules that will ensure full similarity between the behavior of the prototype and its geometrically similar model. This requires specification of the values of all the uniquity parameters, that is, of all the independent parameters for the model flow given their values for the prototype flow. One approach follows from the recognition that the total force acting on a fluid element which results in its acceleration is the vector sum of the various forces such as pressure force, gravity force, viscous force, etc. Similarity requires that not only the total forces on the prototype and the model be scaled by unique scale factor, which depends on the scale factors for mass and acceleration, but the same scale factor must scale every component force that make up the total force vectorially. Thus, if the total force in the prototype is the sum of these three forces: pressure force, viscous force, and gravity force. The vectorial sum of these gives the total force. Then in the model, every force would be scaled by the same scale factor, their directions are remaining the same. So it's not only the pressure forces have the same scale factor, but the x component of the pressure forces also would have same scale factor. The y component of pressure forces would have the same scale factor, the direction being the same. Similarly for all forces. This is the basis on which we construct the modeling rules. So the method consists of identify the various force components that determine the net force at a point in the flow field, obtain the scale factor of each of these force components using the physical laws that govern the phenomena. Then equate the scale factor so obtained to the net force scale factor Kf obtained from Newton's law of inertia. This last is termed as the inertial force factor. And then obtaining the non-dimensional pi numbers in terms of the characteristic independent quantities from the relations established in the step above. These give invariants the pi numbers that establish the modeling rules. Let's do an example. Let's find out the scale factor for viscous forces. Viscous forces are shear forces, which will be shear stresses times the area. The shear stresses, tau, varies like mu dV by dy, the Newton's law of viscosity. So K tau would be K mu Kv divided by Kl. In K area, we have discussed earlier, is Kl square. So from this, we get the scale factor for the viscous forces, K sub F comma mu. The scale factor for viscous forces is equal to K mu, the scale factor viscosity times the scale factor velocity times the scale factor for lengths. And from this, we obtain a pi number F mu divided by mu VL, where the characteristic nature of the quantity is understood. Then the value of the prototype must be the same as that in the model form. We obtain modeling rule like in this table. For the inertial force, we already obtained the pi number as Fi divided by rho L square V square. For unsteady flow, Fu is mass times the acceleration dV by dt, the unsteady acceleration. And this gives you Fu, the scale factor of Fu, as K rho KL cube Kv by Kt. K rho KL cube for K mass and Kv by Kt for dV by dt. And so this gives a pi number Fu divided by rho L cube V by T. We had just obtained the scale factor, the pi number for the viscous forces. Similarly, for gravity force, pressure force, surface tension, compressibility, and for the centrifugal force. You are advised to verify these pi numbers. Now, we equate the scale factors for the various components forces to obtain the modeling rule. For example, when we equate the total force scale factor to viscous force scale factor, Kfi is K rho, KL square, Kv square, Kf mu as shown was K mu, Kl, Kv. Simplifying, this gives you K rho, Kl, Kv is equal to K mu, or K rho, Kl, Kv divided by K mu is equal to 1. And from this, I get rho Vl by mu as an invariant. That if the two flows are to be similar, the value of this parameter rho Vl by mu should be identical in the model as its value in the prototype. From the various component of forces, we obtain these pi numbers which are often used. There are more pi numbers which occur, but we have taken only a sample that commonly occur. These pi numbers are named in honor of the great scientists who have contributed to fluid mechanics, and they are denoted by the first two letters of the names of the scientists. For example, the pi number that is obtained by equating the scale factor of inertial forces and viscous forces is called the Reynolds number, written as rho Vl by mu, and is abbreviated as Re. Froude number is equating the scale factor for the inertial forces and the gravity forces, and we get V square by Gl, the square root of which is termed as the Froude number. So V square by Gl is Froude number squared. By equating the scale factors of inertial forces and pressure forces, we get rho V square by delta P, which is inverse of what is called the Euler number. The Euler number is defined as delta P divided by rho V square. Similarly, the other numbers, Weber number relates inertial forces with the surface tension forces. Cauchy and Mach number relate inertial forces with the compressibility forces. The Strouhal number relates inertial forces with the centrifugal forces and the unsteady forces. Let's do an example in which we need to match Froude numbers. A seaplane is being designed for a takeoff speed of 100 kmph. The model tests are to be made on 1/10th scale model. At what speed should the model be towed to simulate the takeoff conditions? And to determine the thrust needed by the prototype at the takeoff, if the force required to drag the model seaplane to take off is 9 Newton. When the aircraft is taking off, it is experiencing the resistance in water. Here, gravitation force and inertia forces are important. The inertial force scale factor was determined earlier as this, which is nothing but K rho, KL square, KV square. The gravitational force scale factor was the scale factor of mass, which is K rho, KL cubed times Kg. And by equating these two, we get a similarity rule as Kv square divided by Kl, Kg should be 1. And from this, we form a pi number, V square by Gl, which is nothing but Froude number square. So, the modeling rule is V square by GL in the model should be equal to V square GL in the prototype, where the characteristic nature of these parameters are understood. So Vm is Vp into Lm by Lp square root. Now Lm by Lp is 0.1. So that the model speed is 31.6 kmph. Instead of 100 kmph for the prototype, we need to drag the model aircraft as 31.6 kmph. So we will need the force required to accelerate this to 31.6 mph. The force required, the thrust is a force, so it should have the same scale factor, k rho, kl square, kv square. Converting it to a pi number, thrust divided by rho L square V square must have the same value in the model as in the prototype. So from this, thrust for the prototype is determined as 9 kilonewton compared to 9 Newton for the thrust in the model. Thus, we have been able to use the scale factor for developing both the modeling rule as well as the prediction rule. Thank you.